Come on.
All right, guys, this is 13.4. It's on differentiability of multivariable functions. This shows that this limit, well, it's got to equal 0, I guess I should add. We want to show that the function is differentiable by showing that this limit equals 0. And delta f is very much like you remember it from the limit definitions, where you do x plus delta x minus f of x, or x plus h, that kind of idea. We're doing x plus delta x, y plus delta y, and then minus f of x, y. Then we'll subtract the two partial derivatives times their respective deltas. And the limit, and when we divide by the distance for the deltas, god damn it. Let's do this. There we go. Once we subtract by the distance for delta x, delta y, or divide by the distance, fuck, I'm just not on my game this morning. Divide by the distance for delta x and delta y, well, we should have a limit of 0. So just to make sure you're getting nudged in the right direction, delta f here is x plus delta x squared plus y plus delta y squared minus x squared plus y squared. That's my delta f. Let's work on that for a minute, a couple minutes, and then we'll do it together. Oh, I'm missing the. All right, so I wrote out delta F. I wrote out F, the partial with respect to X times delta X, the partial with respect to Y times delta Y. And remember, to do this, we need to, I guess I should bring the formula back down. We need to subtract the partial derivative. So I'm going to do subtraction right there. Now let's just see what we end up with as our numerator. So the numerator in that limit up there is, well, the 2x delta x, these cancel. The 2y's and the delta y's cancel. The x squared minus x squared, these two cancel. And the y squared minus y squared, that cancels. So our numerator is just delta x squared and delta y squared, right? So that's our numerator. We're going to do the limit as delta x, delta y goes to 0. And we're dividing that by the magnitude of delta x squared, delta y plus delta y squared. Which just cleans up to delta x, delta y going to 0, 0 of the square root of delta x squared plus delta y squared. We have no problems plugging in 0, 0 here. We get the limit is 0. So f of x is differentiable at 1, 1 or 0, 0. Now, I asked to show it at 0, 0 and 1, 1. Did I ever actually reference a point in my operations? Did I ever have to plug in 0, 0 for x, y?
No.
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 So this was true for any point. So this is the same thing for 1, 1 as well. So f of x is differentiable everywhere. That was fun.
Oh yeah. Yeah, when you look at it, it wasn't actually all that bad.
I mean, once you move the delta f is, it's just like a general formula we're supposed to remember.
Yeah, I mean, that's part of linear approximation, I think, as far as I can remember.
Yeah, I heard linear approximation last night.
No, it's a long equation to remember and to write it down. It doesn't matter. Especially when you enter into the dx.
And I've got more fun when you're ready.
Oh, this class is ready for anything.
So you'll notice that if I come back up to this formula up here, if I factor out the minus sign and just put the minus sign outside of like parentheses, I've got that. The partial with respect to x, delta x, plus the partial with respect to y, delta y. That's called a total. When we switch it to d's rather than deltas, we have a total differential, which is our next section. If anybody needs this up, I'm about to take it away, so let me know. If you need it up longer, let me know. Otherwise, it's going bye-bye. We're going to look at total differentials.
Good.
All right. Let's do it. So total differentials look just like the thing with the delta x, except now we have dx and dy. So when we're doing here, what I've got listed is z is a function of f or x and y, and w is a function of x, y, and z. And I know that I can write that a little bit cleaner looking.
You can just go back to what you had.
So we want to find the total differentials. We'll start with this nice fun one up top.
Again, wait, is that a partial? Or is that regular? The same thing again. Is that a partial?
These are all partial derivatives times dx's or dy's.
They're starting to look like regular D's.
In fact, dw or dw looks a lot like this. It looks a lot like fx, fy, fz dotted with dx, dy, dz. That's what it looks like. Oh, did I bring dot product back out of nowhere? Just boom, bam. Just to keep you fresh, keep you looking for things like dot products where you weren't thinking dot products before. I don't think they point this out in the book, but it's true.
It's just like transformer, assembly or knowledge is from nowhere. Cosine, yes, cosine.
Cosine 6y,
B, Y.
or is it by? Is that 6y or by? I would assume that's a 6.
6.
I'm probably about the only person that would draw a b that way.
Yeah, a B looks more like a B.
Composition.
Yeah, yeah. So you do them a lot cleaner. Mine can, like, if I'm not careful, will kind of look like a 6.
So
Probably 'cause
don't
I
write lowercase b's. That's a secret. If your lowercase b's look like a 6, use your b's as capitals. Like my t's look like a plus sign, so I don't write t's.
Oh,
I
well,
write typewriter t's,
well, I actually learned
contrary to
do
what
that.
Lawrence says.
Actually, it's funny because I actually learned to do that last semester because we use T so much
Seems just.
Yeah.
to draw my T's with a little curve. Because they looked like pluses too much. I was like, this is getting really annoying. So I started doing with the curves, and my writing is slowly but surely getting slightly, ever so slightly better.
You'll notice I only do t's like that when I'm doing equations. Like you can see t's in my sentences and they do not have that tail.
Well, oh, really? Yeah, because I do that in my sentences as well. My T's
It
look
slows
like
me
that.
down to do t's like that.
Now, why there's like two different.
First one is 2 variable, second one is 3 variable. They just do the formula. That second one is for
Be a
B,
messy part.
so I should be.
So what's the partial derivative of z with respect to x here?
Negative 3 of 3x cosine 6y.
That looks good to me. And f of y.
Negative 3 and negative sine 6y times 6.
Just being negative.
Negative 6, blah, 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 sine.
Wait, wouldn't that be negative 18 because you're multiplying the 6 by the 3? Oh, I'm looking at the wrong thing. Never mind.
We're not doing the mixed partials.
That's my problem. No, I was looking at the wrong equation, thinking of the original.
Check deducted.
Maybe I should put that in parentheses.
Yeah, that looks awesome. Good.
Is that dy and dx in the UZ of partial, or is that? Or do we have to differentiate particles? The same thing? Or am I?
No, you're not. Mr. Jones, Lawrence was
Yeah.
wondering how you came to that idea of DZ.
Are those like, why is it a partial of x, like, is that dx like another partial of x, or?
No, it did. This is very much looking like dz dx, but having the dx on the other side. You did this with dy dx too. You would have dy dx equals f prime of x, but the way we did differentials in Calc 1 was f prime of x dx. This is just a two-dimensional version of it. This was Calc 1 differentials. And it always, to me, looked like multiplying dx to the other side. It still looks like that to me. That's not technically what's going on, but for all operational purposes, at least for the Calc 1 version, it is. You'll notice that doesn't scale up to dz. So, and this is not in the book. It's not even important. I was just pointing it out, so I'm erasing it. The important thing is that when you do total differentials, you do partial derivatives, partials times d variable. That's my shorthand notation for saying dx or dy. Now we want to go bigger, and let's do a three-dimensional one. I think I want to motivate that or say that answer a little bit more to your question, Lawrence, because there was more to the Calc 1 version, and I want to add it in just to make sure you guys were all on the same thing. When you first started doing df dx or dy dx in Calc 1, you really started with delta y delta x. And delta y delta x is that slope. It's the f prime of x. And then we went on to say dy dx equals f prime of x. These two are approximate. This is approximately that.
Right, no,
This-
yeah, no, that's not what the confusion was. The confusion was, I was just wasn't sure if you meant to put like a partial x, like instead of
Oh
dx.
yeah, it was very deliberately partial.
Yeah, I just maybe thought like you were being like a little lazy with the curly part or something.
So dw is df dx dx.
Right, yeah, no, that makes sense.
Okay. Because I don't know how much you all remember from Calc 1, but from some of your guys' tests and derivatives I've seen, not everybody remembers everything from Calc 1. And that was the less easy part to remember.
Like just get intervals and derivatives mixed up.
Again, I'm going to write out doing fx, fy, and fz individually and then put them together. If when I were doing it and comfortable doing it, I would bypass that and just go straight to the total differential. And hopefully one day you guys will get there. But for now, I recommend just writing them out piecemeal.
Yes, we have a question.
What happens to the plus C in the in FX and FY? Should it still be there?
Constant.
Z is a constant with respect to X and Y.
Oh, there.
Again, so it's zero. Zero for the teams, so.
Did everyone get those?
Yeah.
All right, so let's assemble DW.
On FC, we seen a power on Y.
I actually go at third.
Good catch, Eric. As a reminder, what partial with respect to X, Y, and Z means, this is like the change in the I hat direction. This is like the change in the J hat direction. And this is like the change in the K hat direction. So things that are parallel to our unit axes. Are you stretching, Jericho, or you got a question?
Oh, it's stretching.
Where we're going with this is just like we did with the tangential and normal and binormal. Not everything is in IJK, and that's not always a useful coordinate system. So not 13.5, but 13.6, we start looking at going in any direction, not just along the IJK axis. And if you're reading Discord, or remember in Discord, that's where we start talking about the gradient, which Mike was so fond of. And it sounds like Brandon's really fond of too.
I don't remember it being hard. I don't know what he was talking about.
I don't think it was that hard either. I thought it was pretty straightforward.
And I remember Lagrange's multiplier being really useful too.
I actually remember thinking it was really cool. Like once I understood what it did, I was like, wow, that's pretty neat.
Yeah.
All right, so assuming you got that one done, why don't we make it actually hard? Oh, what?
Oh, hard. Oh yeah.
We'll just keep it to two variables, X and Y. But
It's not hard.
let's kick our game up a notch.
Oh, that's a
Because I noticed that chain rule and product rule wasn't necessarily people's forte. And so we want to practice up on those skills before the next exam, and I crush your souls.
I mean, at least you're not doing it to like three differentials at once.
That's just too much. I mean, I could. I like how
You
you're
say that,
thinking.
but-
Should I make this a W and throw some Z's in there?
Yeah, might as well.
Well, that's not what I meant, but okay. Because I was saying that I had to do this like, what was it like?
Maybe we'll do that next if we get this done in time. I need to give you guys a little bit of time for this one. This is a little bit longer.
I'm just sharing my fun experiences in differential equations. Ripple product finding third order differential.
I actually already sort of did this with 3 variables, Brandon. It was called the bonus question on the test.
Oh man, yeah.
Chop circuit?
Hmm?
Are you talking about chop circuit? Bonus question?
Yeah, the bonus question on this test.
The
Yeah.
test you guys just took.
Yes,
Yeah,
You guys had to take derivative with something that had 3 different variables in it.
chapter 13,
yeah, I know. But are you saying that you did something similar with the bonus question?
on the last test.
Yeah,
Yeah, on the last
Yeah.
test.
Yeah.
This is similar to the last test, but not like the last test. It was, you already knew how to do stuff in the last test.
Hardly imagine
Just
that.
hadn't done it yet.
I hardly imagine this. It's the same kind of thing.
I'm just waiting. I'm waiting for James to mess up. I'm just waiting for James to mess up so that I can go to his father and go, you haven't done a good job raising that young man. Completely unconnected events or ideas, but it will still be fun to do.
Triple product rule.
This is almost like a, but Mr. Jones problem right here.
frankly, I'd rather do triple product rule than like double or triple integration by parts. Sure, integration by parts just gets really annoying to write at some point.
Rate by parts is good.
Like, yeah,
For integration.
for like Calc3, integration by parts, where you have to do it like multiple times.
See, I always thought that was neat. It was tedious, but the first time I recognized that once you did it twice and you got back to something in the beginning, that you had to make sure you followed everything right, and then you could get the answer. You never got an answer in and of itself, but you got the answer through repeatedly integrating by parts. I thought that was neat. The same way I think gradients are neat.
It was kind of neat, but it didn't really feel all that neat when I had to do it over and over with like several problems in a row. But yeah, thinking back, it was pretty neat to look at.
Looking back at it, it's cool.
But it wasn't very cool when you're doing it.
Same reason I like separation of variables. Separation of variables was a mind bender. When I realized what it did, I was like, ooh, that's magic.
Oh, you mean for like solving differentials?
Yeah,
Oh, okay. For some reason that just feels really intuitive to me. I think that's just kind of sunk in too much to me. Because that feels way too intuitive at this point.
I don't think you appreciate the magic of separation of variables then. Because I've
Yeah.
known how to do it. I didn't say it wasn't easy to do. But the math is, well, no, it actually is not easy to do.
Well-
Maybe at the easy, simple level you're learning. Separation of variables on a big scale leads to things like Bessel functions and stuff like that. It's not
Oh,
pretty.
yeah, I probably have not gotten that far. No, I end up getting, usually I end up getting pretty lazy and end up using like something like integrating factor instead of, because it's usually between those two that you want to choose, you can choose from. And integrating factor always just kind of feels a little easier to me. There's a little less thinking.
I don't even know.
Yeah, integrating factor is not separation of variables.
No,
That's actually kind of neat too, but not too hard.
no, it's
I
not.
like the idea of working backwards on that. I think that integrating factor is pretty cool. You guys will get
Yeah,
there. That's next semester.
Yeah, I love the way that actually works and how it like just gives you the product rule every time so you can easily integrate it. I think that's really neat.
Let's make sure people are doing stuff to right. I'll do f of x real quick. I'm gonna break this into 3 parts and do the derivative of each one at a time. So I've got y squared exy sine of xy. Maybe I'll change colors as I'm doing it.
Trying to start though.
And then we've got plus this one. The derivative with respect to x there brings a y down, and I've got xy cubed now. And then maybe I'll do this third component in green. We take the derivative. We also got to do the chain rule and go inside, take the derivative, bring a y out again. So, and derivative of sine is cosine. So we'll have xy cubed e to the xy cosine xy. And I made it kind of simple with the later functions with the product rule by keeping it xy rather than like xy cubed or some shit like that. If we jump to fy,
Well, that's it.
If you want to make your life a little easy, you can probably factor out the e of x, e to the xy for each of them.
that just means doing an extra step at the end that you don't need to do.
It's up to you. I was just saying that it's something if you want to do less writing.
Now we do the red one. We bring down an x.
I guess for the C.
And then we're taking the derivative with respect to y. We bring out an x here.
Right.
And derivative of sine is cosine.
Yeah, that's a lot. Why is there?
Nice. I like it. Just put exactly question on the tag.
Why is there a 3 on the
Don't change anything, please.
So now, rather than rewriting all of that, what I'm going to do is erase these portions and say dz equals
Oh, I forgot about the.
Wow, that's
like a
great
cheater,
place.
It's sure.
I didn't follow it.
Man.
like a total cheater. That looks sloppy over here. I'm going to redo that.
At the bottom, you could have just said where dz is the summation of fx and fy.
Sound like the physics.
Physics.
Yeah, I mean, pretty sure Quinn will do it.
Only.
I thought I was like, okay.
Can you go over again how you did those product rules so like quick? It's
Oh.
like,
Yeah, I the way I do product rules, like this is effectively, if I say A is X squared, no, fuck it. We're not using A. Smiley face is XY squared. Frowny face is E to the XY. And I don't know, flat face is sine of XY. Nope, that's too much work. I don't want to drive faces each time. We're doing A, B, and C. As much as I want to use them, it's tedious when you're doing it a bunch of times. Z ends up being A, B, C, the way I wrote it. So I just do this. I switch one. I write the things 3 times. And I switch which one has the derivative on it. I just go left to right along the derivatives.
I was trying to.
That probably should be DC, by the way.
wait, so you don't have to
Do them
product rule or what?
and then do the product roll
There you
value thing, stuff.
That's triple product rule right there. That's finding the individual derivative of one part, and then doing the individual derivative plus adding the individual derivative of another part, and then adding the individual derivative of the set.
Is it allowable to like differentiate, like say like, if you just found like you just ignored the sine XY and then found the product rule the first two, then product rule that with the last one, is it the same thing?
So another way of doing this, sounds like what Lawrence is asking. That's the same thing.
Oh, yeah.
Okay.
And actually, there are times when doing it this way will actually make the problem so much simpler.
It seems
In
like
fact,
this
this is how Ben did his extra credit. He didn't put AB, he put smiley face there. But he did his his derivatives like this, where he didn't do it all at once like I did. He broke it into two steps like this. Because it worked well, he had rho sine phi in here. Rho sine phi inside the parentheses rather than doing both rho and phi. He left it like that.
No, I
It
think
was pretty clever. I give props to Ben for doing it that way. Made it nice and tidier. Both methods work though, Lawrence. I think this one, because then you still have more to do here. This one, you still have to at this point go, okay, well, now this is A prime B plus AB prime times C plus ABC. So like this requires more than one step doing it this way. If you just like treat them like 3 different functions and shift what you're doing the derivative on each time, not only is it you're staying in a sequential order, it's only it's all one step.
I think that way of doing it is useful when you're able to make it less of a triple product rule that's more manageable. That will like maybe lessen the load on a part of the function that would cause it to be a triple product rule. But those are very quite circumstantial.
Now this method right here, this DZ right here on the bottom, is actually pretty helpful if we make the C. Don't put them in order, make C equal e to the xy here. Because then C and C prime are close. C prime is just, there's another coefficient times C. I fucking wish I wasn't using C here. Okay, so maybe like saying we take the derivative. I guess I gotta do X and show Y. This is Y e to the XY, and this is X e to the XY. But this is just YC, and this is just XC. So like doing it this way, when you have an exponential, it kind of gets helpful because you can factor out that exponential, like Brandon was saying. But you have to make sure you do it in a specific order to make that useful. The way I go quickly is I just do this thing.
Okay.
You'll make the least mistakes doing it that way. It just means that you'll have to write more.
Yeah.
I think I'm more prone to making errors this way. To me, I am more error prone this way because there's more steps. And more steps
I-
means more chances to fuck up.
I might do that if like I feel like I really need something much simpler to work with a long problem that I know is gonna turn into a huge mess. And I want to try to minimize the damage. That's when I tend to use that type of idea.
Other than that, it's 8:59. I know you guys got classes to go to.
Still out of town, maybe.
We will do more with 13.4 tomorrow. In fact, since I know you guys are liking these differentials, we'll do another one tomorrow.
I'll be holding my regular SI later today as well.
I would go, dude, but I have work every day.
Take care too.
Don't worry
That's
about
why I haven't been there. Same with physics too.
No, actually, Mr. Jones, on that topic, you know, I think I told you about how I have a class only lasts a half a semester, right?
Uh-huh.
Yeah, so I was thinking since from what I'm hearing, there are like my SI kind of mixes in with one of the physics classes as well. Yeah, so
We
I
can
was
change what
thinking
hours you
about-
do it if you want. Just let me know when we're doing them.
Yeah, when I can't do it until like after the 15th, which is basically so I can make sure my timesheet is correct and there's not like so many concerns
I don't know.
there.
I was thinking about actually working on a little bit of the.
Okay.
But
I don't think-
I'm thinking
since
of
it's not gonna be till, like,
sending out a poll to see if people want my
So, yeah, I'll
Fridays
probably,
or
yeah.
something to Wednesday, move my Fridays or something to Wednesdays or anything.
Okay. That works.
That's what I was. And then like maybe moving my Monday hours forward or something. Now that I can understand like the schedule I have throughout the week and I know what I can work with, I feel like I can be more flexible with my times.
Okay.
Have a good day.
Just throwing that
You
out there.
too. I'll see you guys tomorrow.
Did you guys have any questions? Okay, I think they're good. All right, I'll see you tomorrow.
Okay.